So this is the work we have just started on formal specifications of RISC-V instruction set. Let me give you a little bit of a background of what this, where I'm coming from in this. So I've joined up with Professor Adam Chipala, my colleague, and the slogan is chips with proofs. So chips will have very definite specifications, and we like to show that the chip we are implementing actually meets these specifications in some formal sense. And we are not talking of toy chips here. I mean, they must boot Linux. And we want to deal with real implementations. We are willing to adjust our methodology for designing correct chips, but we are not willing to compromise on the quality of chips we want to produce, the architectures we want to implement. Okay, so now comes the most important part. Both the chips and the proofs must be highly modular. What do I mean by that? We all understand this in design flows. You know, if you're designing a complex things, you design simpler modules and you connect them together and you hope that the whole thing works according to some specification. But now we also want to do that at the proof level. We like to prove these components correct. So each component must have a specification, and then we would like to compose these proofs just as we compose things when we design hardware. Now, what that implies is that we need modular specification. Most concerned about microarchitectural issues, memory issues. In my own personal work, not at all concerned about arithmetic, which is not that it's not important, but it's a different subfield, and that's not, we are spending any energy. So the main point here is that we can't do any of this unless we have specifications for ISA, right? And these specifications have to go beyond just some written document. They have to be executable, machine readable, etc. But there's some subtlety in this. It's not as simple as saying that we must have an interpreter which is automatically generated, which I will explain. Okay, so we strongly prefer operational semantics as opposed to axiomatic semantics, because as engineers, for me, it's easier to argue, right, what's going on with operational semantics. With axiomatic semantics, there's always this danger, did you get them all right? You could have easily missed a few axioms, and then its semantics in some sense is incomplete or underspecified. So these semantics have to be specified in terms of simple machines, simple abstract machines. And this is, again, a judgment call, but a very important one, because I'm seeing lots of operational semantics being defined, which are so complex. You know, the machinery itself is so complex that from my point of view, it's not satisfactory. We need much, much simpler machinery for that. And here is some notation. I apologize that, you know, I'm going to put up some notation of this sort, but this is just to give you an idea of what kind of theorem you may want to prove. So the upper thing here says if you have specification for a memory and if you have specification for a processor, right, and given these specifications, if you implement them and then combine them, right, that should be the same as if you combine them first and then give the, you know, derive the meaning of that, right? So that's all the first one says. The second one is much more important, and that is about modular refinement. Suppose I have processor Pi, which I refine into Pi prime. Okay, everybody can see that? So Pi prime satisfies whatever Pi was doing, and what you would like to prove is that Pi prime plus memory is still going to work correctly as Pi plus memory. In other words, I'm only modifying part of it, and I do not want to prove the whole theorem again. If I already knew that this was working correctly, I change one part of it, right? And I say, no, I'm still under spec, then the whole system is guaranteed to work correctly. So these are the kind of goals we want to have in our work, and we are actually pretty strict about this in our own work, in our own implementation, that we will do lots and lots of modular refinement. You know, we'll implement the system, then we'll take one module out and refine it further and further and so on. And We are expressing all designs in BlueSpec primarily because it provides atomic actions, and of course, it has very strong notion of types, etc. So you don't make silly mistakes of that sort. But these atomic actions are pretty important for defining semantics also, because after all, what is an instruction? An instruction is simply an atomic transformation on state. Given some state of the machine, you're saying how a given instruction will transform that state. So this matches very well with what we are trying to do over here. Now, what will happen in our system is that we are also going to sort of express both the specification and the implementations in the same framework. So that sort of simplifies some, you don't have to jump through as many hoops and proofs as you would have to. Now, Professor Adam Shipala is developing a whole framework for doing these kinds of proofs, and this system is called Kami. So this is like mechanically checkable proofs in Coq. And if you want, you can think of Kami as a subsystem within that framework so that it's easier to do these things. Now, a word about BlueSpec. You can think of BlueSpec programs or designs as a collection of concurrent objects. Each object has its internal state. If you want, you can think of it in terms of registers as that state. And each object has interface methods, just like in any object-oriented language. You can manipulate the state, you can observe the state only via these methods. What is new here is the notion of you have these atomic actions which can work across, they can work within a module, they can also work across the module. The same atomic action can call methods of many different objects. So the system is such that it will allow you to compose very complex atomic actions across many, many different modules if you follow these semantics. Okay, so now some other restrictions on what I want to do. So when we talk of specifications of ISA, I absolutely want to avoid the following concepts. So for example, I don't want to think in terms of partially executed instructions. If you're giving me semantics of an instruction, it should be the whole story. Give me this instruction, how does it transform the state? Now, this may seem obvious to you, but I'm telling you, by the time we get to load and store instructions, this is extremely hard to do. You know, people get stumped by how to do this. I also don't like concepts like a store has been performed with respect to something, something, right? Because there are so many events people define that even as an expert, my head hurts after a while. I can't keep these definitions straight. So I want much, much simpler ideas than that. The second point I want to make is non-determinism is essential in specifications these days, right? So you may not think add instruction needs any non-determinism, that is true, but the moment we are talking of multi-cores, certainly loads and stores from different processors are interacting with each other, right? There is a range of behaviors defined, but not everything goes in this, right? So non-determinism we have to be able to capture. Similarly, even in a single processor, the meaning of fences shows up at non-determinism. If you leave out a fence, then there is a range of behaviors that are possible, right? And if you put the fence, maybe there is only one behavior that is possible. So to capture non-determinism in specifications is essential, and that's where the problem comes in, that we can't write simple interpreters anymore, right? Because interpreter is one sequential execution of the program, while if you want to explore what all can be done, then you need to explore the non-deterministic space. Unspecified behavior is not kosher, right? So non-determinism, yes, but unspecified behavior is not okay. So for example, in parallel setting, people often want to say that, okay, we'll only worry about data race-free programs. Well, that may be a very good software guidance. You should write those kinds of programs. But that's not satisfactory as computer architects. What if you don't give me a data race-free programs? Does that mean that fire can come out of my microprocessor, right? I mean, so there is some range of behaviors that are allowed. Non-determinism, yes. unspecified behaviors? No. I mean, we have to specify behaviors for all programs. We will use, and this is one of the contributions we are making here, we will give semantics in terms of what I call I squared E, instantaneous instruction execution, right? You will pick up an instruction and you will execute it completely. No partial execution of an instruction. So let me describe I squared E framework for you. It's very obvious what you will do in I squared E for add and subtract instructions, so that's not I want to talk about. I want to talk about loads and stores. So one memory model all of you know is sequential consistency, but before I go, let me just give you the basic tenets of this I squared E model. You pick up an instruction and execute it completely. What do I mean by that? It modifies the processor state in a deterministic fashion. Okay, so that's one part. The second part, and by this I mean the processor state in every processor is always going to be up to date, right? There is no question of reconstructing the state. It's by definition always correct. The second point is I want to think of memory as a monolithic block. Please don't get confused with implementations, right? This is the definitional framework, how you're going to define the ISA in this. So, of course, in your implementation, your memory is going to be highly pipelined, etc. But in my definition framework, memory is always monolithic. It has n ports, and anybody knows what that means. You go and write something, that means it instantly gets updated. You read something from any port, you get the latest value, back from there. Data moves between processors and memory in an asynchronous manner. Okay, so this is the trick, right? So processors are deterministic, memory is deterministic, but when the data moves from processor to memory, you can toss a coin, who gets to go next, right? And that's how the data will move between processor and memory, and you'll be amazed what all we can do with just this trick, that everything is deterministic, but some data movement is non-deterministic in the system. And then, in order to model more complex things, more complex memory models than sequential consistency, we'll allow you to put some, I don't know if I can, So you can have some more state inside every processor, which is still processor specific, not part of the memory. Memory remains monolithic. And a basic problem arises in these things is because there are multiple paths to the memory. In this example, it's trivial, right? You have n processors, so there are n paths going to the memory. Now, I'm going to show you some tricks we use to define these things in the multiprocessor setting. But my goal is not here to talk about memory models. My goal here is to show that some of that technology is needed even to define semantics of a single processor. So before I go to that, let me just take you through one or two slides on memory models. So all of you know sequential consistency. It's the model we all love. You have a monolithic memory connected to n processors. What is the semantics? Pick one instruction from one processor, execute it. Okay, add, you understand. Load, okay, so just go and read the memory, and that's the value you get. Store, you just go and update the memory, right? So this is the definition that Leslie Lamport gave, long time ago, right? And if you want, I can write it formally, right? So again, you don't have to read all this, but basically you have first rule corresponds only to non-memory instructions. You just decode it and you execute it, you're all done with that. And the load instruction goes and directly reads from the memory, right? If it's a load instruction and store instruction, just go and directly updates the memory in this case. Okay, so we can write down these rules. These rules are atomic actions. What is the effect of this instruction? Now let me go to a slightly more complex model, but still pretty simple, and that is the model used by all the Intel machines, TSO model. So in TSO model, what you have to do is you have to introduce this entity in your abstract machine, which we'll call store buffer. It's reminiscent of what happens in real machines, but it doesn't have to be. This is an unbounded store buffer. There is nothing to do with the size of it. Okay, so how does this TSO thing work? As long as you have a non-memory instruction, no problem, right? Just execute it. But how do I execute a store instruction in this? So in this machine, the meaning of a store instruction will be you pick up a store and you put it in store buffer. That's an atomic action, right? You just take something, a store, and you store it in store buffer. Nothing to do with memory. It's a local action. The store instruction is done at that point. How does load instruction work? You have a load in a processor. You will first go and read the store buffer. If you find it there, you're done. If you don't find it there, then you go and read it from the memory. So again, the whole thing is absolutely deterministic, atomic, et cetera, et cetera. The trick is that how do I move things from store buffer to memory? And that's an asynchronous action going on in background. So you take the oldest thing in your store buffer and move it to the memory. All right? If you had a PSO kind of machine, you will do it slightly different, but that's the meaning of this. Now, what is amazing in this system is I did not talk of any reordering of instructions. You take one instruction, you execute it. You take one instruction, execute it from any processor. But now the behavior, because of this thing in the background, will be as if loads can jump ahead of stores if they're not to the same address. So those kinds of effects happen just because we are modeling it cleverly, right? You can derive those as axioms based on this. You can prove those as theorems that, oh, if the addresses, if the load and store are two different addresses, then the load can go ahead of the store in this machine. Okay, so I hope this point is getting across that in my model, there is no reordering going on. As far as you are concerned, you are executing one instruction at a time and updating the processor state. But the model is rich enough that because of what is going on in the background, it can appear as if things happened out of order. Now, in this thing, I can also easily turn it into a partial store order, which was present in some of the Sun machines, where instead of just insisting that the oldest address goes into the memory, you can say oldest on a given address goes to the memory. So you have a choice. If you have store to 100 and store to 200, you can put either of them in the memory. So that's even more non-determinism than you had in a TSO model. Now comes a very interesting thing. So this much has been known for a while. Now I want to go to even a weaker model where even loads can reorder themselves. And that's very tricky. That's very, very tricky. How to do that in this I²E framework, how to do that using instantaneous instruction execution. So I'm going to introduce another conceptual device here. It has no corresponding physical meaning, right? But it captures conceptually all the stale values that may be running around in your system. And this device we will call invalidation buffer. So in every processor now, you have a store buffer and you have an invalidation buffer. So invalidation buffer is summary of all the stale values that might be visible to you. So how does this work now? All the add instructions, you just go and execute it instantaneously, no problem, just like before. How does the store instruction work? Exactly as before, you go and put it in the store buffer. How does load work? First, we go and search the store buffer as we have always done, right? And if it is not in the store buffer, then I have very, more non-determinism. You can either read it from the invalidation buffer or you can read it from the memory at that point. But whenever you read something from the invalidation buffer, then you must delete staler values from it. So there is a notion of how stale a value is, right? So if I read this value, then all the things that are staler than that are no longer visible to me. So they must be deleted. Okay, so that's the whole point of this invalidation buffer. But I didn't tell you how values got into the invalidation buffer. Remember, we had a background rule that we can move things from the store buffer to memory. So when I move things from store buffer to memory, the old value in the memory pops up in all the store buffers, sorry, in all the invalidation buffers. Got it? I move something, oh, I think I have even animation. Yes. Okay. So when the value moves from store buffer to this, it pops up, the old value pops up in all the other invalidation buffers. You see, this is capturing the fact that just because I updated it doesn't mean it's visible to everyone, right? Because different people may see it at different times. So there are lots of stale values sitting in the system. And the rules for invalidation buffers are very simple. You just go, you are allowed to toss anything out of invalidation buffer anytime you want, right? So no need to worry about that. But now the moment we have these kinds of buffers, I forgot to mention something about store buffer. Anytime you have these kinds of buffers, you need more instructions, fences you need. So in TSO model, we have a fence called commit. So, commit instruction cannot execute until the store buffer is empty. All right, so you just get stuck. Still atomic, instantaneous description, but it just doesn't no op until the store buffer becomes empty. Similarly, I'm going to provide another fence instruction, which I call reconcile, and that cannot execute until the invalidation buffer is empty. So anytime you have read kind of buffers, you need reconcile. That's a way of asserting in the program that, look, man, I want the latest value. I don't want stale values, I want the latest value. So that's saying, please get rid of all the stale values. Otherwise, this machine cannot proceed. So let me just quickly say, why am I telling you this? These issues arise within a single processor, right? Within a uniprocessor. Why? Because of self-modifying code and because of TLBs. Because the notion that you have a page virtual address translation going on. So the fundamental issue is exactly the same. If these things were completely consistent all the time, there will be no issue. But by doing these by not making the instruction memory part of the coherent memory, we create problems for ourselves. So the whole point will be that people don't want to have these two things coherent, instruction buffer and data memory. Why? Because it simplifies implementation, and it's very rare that people do self-modifying code, and usually the distance is very large. So there are many, many justifications why you want this, right? So typical solution is flush the instruction buffer, and that's what the solution in RISC-V is as well. And it's very easy to define such an instruction also atomically, right? So this will be the meaning of it. If you see a fence I instruction, then you can only execute it when the store buffer is empty, and then you must clear the instruction buffer at that point. But notice I have done something here. In my abstract machine now, it has become more complex, that within a processor, I have this new entity called instruction buffer, which I didn't have before. Right? So this is the price you're going to pay. Anytime you introduce new things in your machine, something like that is going to show up in the abstract machine as well. But I can stick to I²E descriptions. I can still give you one instruction at a time. And since I don't have time, let me just tell you that when we do TLBs, similar issue will arise. Because when you do a TLB walk, when you do you're doing the translation, at that point, actually you can go and modify the page table. I mean, RISC-V specifies it should all be done in hardware, but because of usage, because of dirty bits, etc., you can go and modify, and these are implicit writes going on. They may not be visible to anybody, right? So how to make sure that these implicit writes will be visible, when they are done? So ISA description has to deal with this. And a similar kind of thing will have to happen here, that you need some instruction which will make things visible to everybody. And whenever you want to make things visible, you use some sort of a commit instruction. And whenever you want to make sure you are seeing the latest, you use some sort of a reconcile things. So the description of these things will turn out to be that this sfence instruction, if you see it, then it can only be executed when the store buffer is, the TLB part is empty, and at that point you go and clear the instruction buffer at that point. So these kinds of things can be described, and I don't have enough time to go into this, but this has now become a pretty, complex model inside a processor, and there are still many issues to be decided about this, and that's why community has to be engaged. Because if you're going to expose all these things, right, that the TLBs are not necessarily coherent with the data writes you do in the system. In fact, we don't even want to insist there is a TLB. TLB itself is just a performance hack, right, in it. So how to maintain the coherence of this, all this stuff makes the semantics of even in a uniprocessor setting quite complex. And we have to define these things very, very precisely. That's one point. And community, some feedback is needed because there are issues in this where one can decide one way or another. The other issue that bothers me is that if we are going to be building a trusted base, these level of specifications may be just too complex, right? We may want to define a RISC-V semantics or RISC-V more restricted version of it, which will still be sound with respect to the more general case, where you don't have to deal with these internal difficulties that come about because of incoherent instruction cache or incoherent TLB, etc. I'll stop at this point.
All right. Thanks, Arvind. Any questions for Arvind? Oh, sorry, Arvind.
Hi, I'm Vittorio from WDC. How do you plan? How do you model the asynchronous path of the memory?
Sorry, I couldn't hear you.
How do you model the asynchronous communication with the model, since you propose to use asynchronous communication with the memory model and the processor model?
Sequence communication? I'm sorry, I'm not following.
You propose to use asynchronous communication with the memory model. How do you represent that as axioms?
I'm sorry, I'm not getting the question. Can somebody help me?
You said in your presentation that memory has so far been deterministic,
yes.
Everything is synchronous, but the idea would be move towards a synchronous communication memory model. How do you, in your proposal, how do you model this asynchronous communication with the memory model as axioms in your model?
So I think all I'm doing is when we are thinking of memory module itself as synchronous monolithic memory, you're just doing a write and its effect is immediately obvious, right, to the next store. So you always think of doing operations one at a time, so I don't care which port you pick. But if you do a store on this port, it's instantly visible to any load from any port. Maybe that was not the question.
Yeah, there's the background rules that move things non-deterministically, and that gives you the effect of the asynchrony.
So in fact, it's not an asynchronous model behind, it's just non-deterministic.
I think the word synchronous is slightly problematic for me. So you're specifying atomic actions. So you're saying this is what should happen altogether. Internal timing is irrelevant to me, whether you take 1 cycle or 10 cycles or do it instantaneously, right? But the effect is instantaneous. What do I mean by that? Before the next action happens, all the effect of this must have taken place, right? So one atomic action at a time. And by asynchronous, all I meant was that each processor was behaving as if it executed the instruction instantaneously. And this ordering, reordering effect takes place because you have some freedom when you move data from the processor to the memory. And that essentially makes the system behave as if things got reordered.
Hi, I'm Tariq Bashir from UMass Amherst. I have two questions. Just wanted to...
A bit louder.
Yes, just wanted to know your thoughts. How is the verification done in the industry? You mentioned these issues. So how is AMD or maybe Intel dealing with these issues? The second question is, isn't like a verification environment like system Verilog assertions, why aren't they good enough, to express, the kind of issues that you have talked about?
See, I am only giving specifications here. You will have to then build whatever you have in your implementation. You need an exact model of that, right? How, in terms of atomic actions, how you think about that. And then you have to say that whatever implementation does, those behaviors remain inside the behaviors in this simple model I gave you. So that's the verification task. And I certainly don't want to claim that that task is easy. I mean, depending upon how complex your implementation is. We all know how tough it is to prove complex cache coherence protocols correct, right? But that doesn't mean that the specification for cache coherence protocols, I mean, what they're supposed to do can't be very simple. In fact, it is absolutely straightforward because cache coherence protocols at some level do preserve this monolithic memory abstraction, right? But the proof, how your complex cache coherence protocol is meeting this specification can be arbitrarily difficult.
All right, thank you.
Yep.